Hi, I'm Ben-Yaakov. This presentation is entitled Silicon JFET and Low Input Voltage DC to DC Converters. There are some applications that require a low input voltage DC to DC converter. There are some systems like remote sensor that we would like to operate with a single solar cell. And in this case, the voltage, of course, will be low. And then we have the thermoelectric generator that also produces a low voltage, although the current could be fairly high, but the voltage is low, so we do need a low input voltage DC to DC converter. Now in this presentation, I'm going to concentrate on solutions which are based on a JFET, and I'm going to just to explain in a very intuitive way what is a JFET. And let's concentrate on the N-type, meaning that the channel is made of an N-type material. Now the gate is a P-type material. So basically we have here a diode. And the connection here is without an oxide. That is, there is a direct connection here. So if the voltage will be high, there will be a current coming in, meaning that the voltage that you need to have here also has to either be zero or such that the diode will be reverse biased. Now the JFET is a normally on device, meaning that it is a depletion mode device, meaning that with a zero voltage there is a conduction, and if the voltage is negative, then conduction is going down and eventually will be off. So with zero voltage at the gate, there is a conduction. As the gate becomes more negative, we have a depletion region here, and the conduction is restricted, so we have less conduction, and this is really very, very intuitive. And then if the voltage is highly negative, then we have actually blocking and the device is off. So it's sort of in the reverse direction of the enhancement mode, that it is normally on, and in order to control it, you have to have a negative voltage. And here is the output characteristic of such a device. Again, with zero gate to source voltage, we have in this particular case 70 milliamp. As the voltage becomes more and more negative, conduction is going down and down. This is like a FET, okay? A current source in this region, and this is the linear region. And as the voltage will be highly negative, of course, the device will be off. This is actually a zoom on this part here, and we see here this is like an RDS-on for different gate voltages. You have the relationship between the current and the voltage of the drain. This is the linear region, and then you go into the saturation region like a regular FET. I'm showing here part of the specification of this family of JFETs. Okay, we have, of course, the voltages, and then the gate voltage for off, and in this case, like -1 to -4, this is the range of the voltage that the device will be off, and then maximum current, and the resistance, and this will be around gate voltage of 0, which is like few ohms. This is the low power device. That's not the high power device. And of course, if the diode is conducting, the gate diode, then it will be like 0.7 volts, like a regular PN junction. An important parameter is the transconductance, and here it shows 17 millisiemens. Siemens is an amp per volt. And this is for a low input gate that is a 0. I presume doesn't say, but usually it'll be for a zero gate to source voltage. And we have a nice transconductance gain, which is very, very important, as we will see. So what are the possible applications of the silicon JFET? Let me say that there is a silicon carbide JFET, which I'm not talking about. It's a different animal altogether. So we are talking about the silicon JFET. And the most important one is probably that it is a low noise device, and therefore one of the very important applications is low noise amplifier. Okay, this is probably the lowest noise device available, the JFET. And then we have application of current source, chopper, and we are going to talk about applications which are actually oscillators, which can be sort of converted to be a DC to DC converter. And this is the subject of this presentation. So why is the JFET good for low input voltage DC to DC converter? There are actually two reasons for that. First of all, it is normally on. So in order to turn it on, you do not need an auxiliary power supply. Okay, so it is naturally on. And the second reason is that we have gain at VGS around 0, which is very nice because for a self-oscillation, we need gain. So we can have a self-oscillation, an oscillator, even without actually external excitation, but just by a feedback on its own. And this is the idea behind this low input voltage DC to DC converters that I'm going to talk about. And here I'm showing simulation of this particular device. The drain voltage here is 0.1 or 1 volt, and I'm driving it with a 1 millivolt signal of 100 kilohertz to get the transconductance gain. And what we see here is that for 0.1 volt, we have a transconductance of about 15 milliseconds. That's like the data sheet. And with 1 volt drain voltage, we also have this 15 millisiemens, as much as this model is okay. I'm assuming, of course, that it is representing the actual device. So we do have gain at, first of all, around 0 gate voltage, because there is no DC here, just 0, and with low drain voltage, which is very nice and very helpful in building oscillator around it with very low input voltage. So here is a topology of such a converter. I've taken it from this paper. There's been other papers. This is not the only one. It's probably not the first one. There are many, many papers on this. Anyhow, this is just an example that I've taken. And what we see here is the JFET. This is a coupled inductor, as a matter of fact. It has to be a coupled inductor. It's not a transformer because it has to store energy. And then we have sort of a step-up turns ratio. It's 1 to m, so therefore the ratio of the inductances is 1 to m squared. And this is the output, this is the input, and there is an additional capacitor actually to adjust the frequency of oscillation, and that's the whole thing. So what I'm going to do in the following is to explain how this thing works and what are the guidelines for designing it and what can you expect from it. Now, to operate such a converter, you do need a coupled inductor element, and there are many on the market. I'm showing here a coil craft, and I'm showing the one that I'm going to use in the simulation. Well, I'm not going to use the inductor itself, but its parameters. So we have a 1 to 20 turns ratio. We have a primary of 25 microhenry, and so therefore the secondary will be 400 times larger, 22 squared. And then we have the DC part, which I'm not going to use as a matter of fact. And the self-resonant frequency, okay, I'm not going to use it also, but anyhow, this particular unit is 580 kilohertz. I'm going to operate at around 100 kilohertz, so it's okay. And here is something very important, and this is the saturation current of this device. As I've said, this is a device that has to store energy, so you have to worry about the saturation, so it won't go into the nonlinear region, and it is 0.7, much above what we actually need. I'm going also to talk later on about cases in which you have an element which may go into the nonlinear region. But let's now stick to this coupled inductor, which we assume is linear. So here is an LTspice schematics of such a oscillator, converter, DC to DC converter. I'm showing it with 0.5 volt input, although I'm going to run it with various other voltages. And we have this coupling 1 to 20, the turns ratio, and again the inductance ratio is 1 to 400, so we have 25 microhenry here and 10 millihenry here. I'm assuming a coupling coefficient of 1. It'll work fine with coupling coefficients which are lower than 1 with some leakage, but the waveform will have some oscillation, high frequency oscillation, which will corrupt the waveform. And so just for the sake of the explanation, to get nice waveform, I've set it to 1, but it'll be okay if the coupling is not perfect. And then we have the output section, 10K, I'm going to change it later on as you will see, and then filter capacitor. Here, there is a capacitor which actually is adjusting the timing, the frequency, and I've also added a Zener diode. This direction is a diode, and this direction it's a Zener diode, because in this particular design, the voltage can go very negative without the diode, so it'll sort of, in the real system, might damage the JFET. So I've put here a Zener just to clamp the voltage to 15 volts. And here I'm already showing some results, some simulation results. This is for two cases of input voltage of 1 volt and 0.5 volt, changing the load. You see with 1 volt, we get, well, with a load of 100 ohm, which is too heavy for this circuit. The output voltage is very small, but with 1K, we already get like something like minus 2.5 volt. It's a negative output, negative voltage output. With 10K, we already get like 4.5, and with 100K, it's about minus 6 volt. And here, this will be for 0.5 volt. At 100 ohm, it actually doesn't start, but then at 1K, we already got something like, I don't know, minus 1.5 volt, 10K 2.4, and then we get minus 4 volt. So we get a negative output. It's not very high voltage, but still it's higher than with what we have started with. Like here, we have started with 0.5 volt. Okay, so we have quite a voltage that we can actually operate things with it. And here I'm showing a sweep of the input voltage, and with a 10K load, you see that 0.5 we only get a substantial output, and then at 0.7 we get a nicer, and eventually we get something like minus 6 volt for 1 volt and above. So this is a typical performance of this particular unit. Of course, you can build it for a lower voltage, higher voltage, different transfer ratio, and this is just an example. To understand the operation of this circuit, we have to take into account that this is a coupled inductor. This is not a transformer. So a coupled inductor has a magnetization which is actually storing the energy. So we can describe it as an ideal transformer plus a magnetization inductance. However, using for the ideal transformer, again, inductors may sort of mask some of the phenomena. So I'm going to use a different approach. And here it is. I'm describing the ideal transformer by a dependent voltage sources. So this is a voltage source. The output is a function of the input voltage and times 20, because we have 1 to 20. And the input current is dependent on the output current, again, times 20. So this is void of the inductance effect, and this is a pure ideal transformer. And then we have the inductance, the magnetization inductance put here. So I can distinguish here between the current that is going through as a transformer and the current through the magnetization inductance, which has a very important role in the operation of the whole thing. And then I'm also be showing the voltage on the device itself, the drain voltage, the gate voltage, and the current, of course, coming in from the input and the output current. And this is the positive direction that I'm calling it. This is the positive direction. The voltage, positive voltage is here, and positive voltage is here. So this is the notation and direction that I'm going to use. So let's familiarize ourselves with the waveform here that I'm going to go over to explain the circuit and to see the relationship between the waveform and the notation that I've just went over. So here we have the gate voltage. This is this voltage here. This is the zero level here, and this goes negative. Now this is the input and output current and output current of the ideal transformer. I've scaled them such that I've divided one of them, the input, by 20, so the magnitude should be the same, and also adjusted the polarity, just to show that this transformer is indeed operating like an ideal transformer. The current at the input and output is the same, exactly the same shape, although there is, of course, a scaling of 20. Now, this line here, the green one, is the current of the magnetization inductance. This is the positive direction. And here we have the voltages of the transformer, again adjusted, and now it is reflected to the primary. So we see that when the JFET is on, we have a voltage of about 0.4, 0.5 volt on the transformer. The rest of it is on the transistor. And here we see the voltage of the drain. This is the voltage of the drain. Here it is. And when the transistor is conducting, it's about 0.6 volt, and the rest is on the transformer. So these are the positive direction. This is a positive direction here, positive, positive. And now let's have a look now at the operation of this circuit. So I'm starting off at this point where the gate is on. I see that the current of the inductor is high, is positive, and then we have a positive current coming in, so we'll have a current coming out, and these are the direction, the momentary direction. And since these two are going this way, then either this diode or this diode will be conducting, or both of them, depending on the voltage drop. Doesn't matter. The point is that the voltage here is around zero. Okay, so we have a voltage here around zero. These two currents are going this direction, and the voltage on the transformer at the primary is this voltage here, and the voltage on the drain is this voltage, about 0.6 volts. So this is where we at, and this is where we at 1 volt. Now notice that at this stage, the voltage here is around zero, and this is for a steady state condition, and running the simulation, the voltage here is minus 6 volt. So we have across this inductor, here is a higher voltage than this. This is plus and this is minus. So therefore, the IDT is going this direction. So now the current is going to go down, the current of the inductor. And here it is. And we see it indeed going down. Okay, it is going down, and eventually it'll flip over. That is, the current will go to the other direction. It started here, this direction, and then it went here to this direction. So now the current is going this direction. Still, it is a small current relatively to this one. So net current is still going here, and the two diodes are still conducting. So this is why the gate is still on. So we are in the same situation, as a matter of fact, except that now the current of the inductor is actually increasing, but in the opposite direction. Now eventually, this current will become equal to this current, so net is zero. So we have zero current here. There'll be no current through these diodes. Voltage is zero. And if we'll go one step further, where this current is even getting larger, now we start having a current in this direction, and now it goes through this capacitor because the diodes are not conducting anymore, and therefore the voltage of this capacitor is going down. And here we start to see this. At this point, we have now a situation in which we are on the verge of the linear mode, you might say. We have now a positive feedback because the voltage is going down, the transistor has a lower current, and this lower current makes this current smaller. So therefore, the net current, this direction, is becoming larger. So this enhances this flip over. Not only that, we have now a resonance between this capacitor and this inductor. And here we see this resonance effect. So we have now a self-commutation, a positive feedback, which is driving the whole operating point toward negative gate voltage. Okay, this way here. And here we see it here, that it goes this way. And eventually, it'll go into this situation in which the Zener diode is conducting. The voltage here is minus 15 volt. This is the Zener diode. Here we still have minus 6 volt because of the capacitor. So now we have the reverse situation. The current is going in this direction because it is negative, but here is plus and here is minus as far as this inductor goes. So the IDT is going this way, and therefore this current is going to become smaller and smaller in magnitude. And here we see this current going smaller and smaller in magnitude. So the voltage of the gate is starting to rise, and then we come to another flip point in which we are on the verge of the linear mode, and the voltage is going up. The current starts to flow. The current is enhancing this current at the output, so the voltage is actually going faster up until it locks to this situation in which we have conduction of the diode, in which we have a high voltage here, and one step further we have the diode conducting, and we are back to the same point. So you can see that the function of this inductance is very important. I mean, it's not just the transformer, but the magnetization inductance is really playing a very important role in the operation of this converter or oscillator, you might say. And as you can see in this particular case, we have a minus 6 volt at the output. Input is 1 volt, so we have quite a bit of a gain between the input and the output. Now it is possible to add another winding, and then you can get a positive or negative voltage. This will be the power winding, you might say. This is just for the operation of the oscillator, so this resistor could be much larger. And here, this is the actual load. Obviously, you can add an LDO to stabilize the voltage. I'm showing this topology out of one of our old papers. Actually, it's like 20 years ago. And in this particular paper, we're also handling the question, what happens if this coupled inductor goes into the nonlinear region, and how do you model it, and how do you estimate the frequency of operation and the transfer power between the input and output. Now, running this circuit with an added winding, and in this case it's exactly the same winding, you see that for 1 volt, here it is 100K, this is just for biasing, that's not the load. This is representing the load, and you see that in this particular case we have a 5 volt output, which is kind of fairly nice. In actual implementation, this could be actually used as a starter, okay? Once you have a higher voltage, you can actually start a DC-DC converter, say a boost converter, and once you get the 5 volt, this will start running, then it can self-bias itself, and of course the power is coming from here, and as I've said, in some cases, like in a thermoelectric generator, you can have quite a bit of power coming out of the unit, so you can process it here and get a higher voltage as you would need. Now, since there is a need for this type of application, then a number of companies have come up with a chip, an IC that is doing the work, that is, it is a full-fledged solution to a low input voltage. And I'm showing here a device by this company, just one of many. There are other companies more known. I've just picked up this particular one out of the web, just looking it up. I have no experience with it, and obviously there's no recommendation here, just an example. So here what we see is that this unit will start at 0.35 volt, which is kind of nice, and then it has a stabilizer for 2.7 volt. But the nice thing about it is that it has inside a maximum power point tracking. Now, in the case of, say, a solar cell, we know that you'll get maximum power when the input has a certain impedance. That is, you need to match the input impedance to the cell or the operating point of the solar cell. So this has a built-in maximum power point tracking. And here they're showing some efficiency, which is kind of nice. This is for the basic unit. Again, it can be used as a starter. This is a boost converter, by the way. And we see here the efficiency between, say, 50 for very, very low current to about 70. And this is 1 milliamp, okay? That's low power. Again, this can be used as a starter. That's not the main power conversion. And here is the block diagram of this unit. We see that there is a starter inside. This is the inductor. It's connected to the input. This is the started unit. This is the switching transistor. And then we have the main converter, which is using the same inductor, which is, I guess, turned on once there is enough voltage at the output so this thing can start. And so this is the basic idea that I've shown earlier, only that everything here is within this chip, which is kind of very nice. Again, I have no experience with this device. I've just looked it up and saw it on the web. So this brings me to the end of this presentation. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.